Hello, my name is Alan Quillen. I'm a software engineer at Rackspace. Today I'm going to talk about a topic in software-defined networking, focusing on the layer 3 routing. And since this is a Python conference, we'll show some Python on how to do that. So, those of you unfamiliar with software-defined networking, basically if you Google it, there's a bunch of different definitions. So this one's mine. It's just a software abstraction, which from here on out I'll probably, if you hear me say control plane, that's what I mean, that allows apps, devs, and engineers to manage their network topologies, or once again, I would call that probably data plane. So it's a simple explanation. All right, sorry. Didn't mean to offend. You'll find most of what I say offensive, so sorry about that. So software-defined networking is kind of a newer terminology that came out. It's not anything new, as same with the cloud, just a new terminology. Virtualization is not anything new. But since the cloud's been around and now we're pretty much virtualizing everything, we had a lot of new types of problems we had to solve when trying to virtualize and make networking as a service a thing. So the software-defined networking, it's what that kind of falls under. At Rackspace, that's the team that I'm on. I'm on the cloud networks team, which includes, since we're working on the OpenStack Neutron project, if you understand that, and then our implementation of the data plane stuff, which is what I'm going to pretty much go over today. There's lots of different problems in software-defined networking. I'm not going to go over all of them. As I said, I'm just going to focus on dynamic routing, the layer 3 dynamic routing. And there is a problem space in most cloud offerings that, whereas if you have an IP address, public IP address, and you want to associate it to some sort of resource, in the cloud you don't know where the hell that resource is always going to be. And so how do you map that IP address to one resource? If that resource goes down, you want to take that same IP address and map it to a new resource, which could have been spun up in a different data center, in a different a rack, and you getting all the networking, everything like that to work. So to do the, that's really, okay. One of the software-defined networking implementations is Open vSwitch. It's an open source Linux-based SDN. It's what we're going to show today. It is that abstraction as well as the control plane and data plane for managing the routing on a specific host. It's used a lot in a lot of the virtualization stuff, which is like Zen server, others. Looking to my team for a lot of letting me know if I'm right or wrong on some of this stuff. So. And the package we're going to talk about that's in Python is called Ryu, or Ryu. I'll probably say Ryu and slip up because when I was looking at it the other day, I forgot it's actually pronounced Ryu. It means flow in Japanese. And it's a Python abstraction on top of OVS. It supports other stuff as well, but really it's designed for OVS and supports multiple protocols. The one we're going to talk about today is OpenFlow. And OpenFlow 1.0, but this is supports all the way up to 1.5 as much of what is implemented in OVS. It's a app-based framework, meaning it will every Ryu app that is spun up is run in its own thread or pseudo green thread. So you could spin up a bunch of these apps that'll work independently and communicate back and forth. So. Some other stuff. It has some built-in tools, BGP, and we're not going to talk about BGP today, but I will show a REST web service, which allows you to manage the Ryu controller. Okay, so I'm not going to talk a lot. I'm just going to show you this demo on how a lot of this works, and I'll set up what we're doing. The tools we're going to use are OVS and Ryu, and some of the stuff I'm going to show you, if you're not familiar with it, you can talk to us afterwards. My whole team's here, so we use all this stuff every day, so we can answer any questions you want. If you're not familiar with Mininet, Mininet is a package that allows you to simulate different network topologies. And then OpenFlow 1.3, and I don't know why I have Mininet on there twice. So our test topology is this. So the top two nodes are going to simulate what would be a public host somewhere on the internet. You're running at your house or something. The northbound bridge will simulate pretty much all northbound switching infrastructure. So that would be switching infrastructure at your ISP, as well as your company's public switching infrastructure. So that would be routable from the public. And main is our OVS bridge, and then the southbound stuff could be whatever you want to, whether it's tunneling, switchings, or just whatever. And then these hosts right here are going to be our hidden hosts that only have private IP addresses, don't have public access, and are not accessible via the public. So what we want to do is we want to be able to take a public IP address and route it to one of these hosts. And so we're assuming that these hosts are anywhere. We don't know where they're sitting at.
Are you talking about basically an ACL?
No, you could use ACLs for this, but that's a lot more management. The problem with using those is you don't always know where you need to apply those. So if your host is spun up over here, but you thought it was over here, you need to, in order to do this dynamically, you'd have to first figure out where it's routed to, and then apply those. You could. That's not what we're doing. What we're doing here, though.
Okay.
Yeah. So basically, OVS is it abstracts away the physical interfaces with virtual routing built in it. So the way that works is when a packet comes in and inspects the packet, if it already knows its data path, all that's done in kernel space. It just spits it out the correct interface. If it doesn't know, it bumps up to user space into the flow tables, and we'll talk about the flow tables in a second. The flow tables define your routes. If it finds a route in your flow table, it builds that data path and then spits it out the correct interface. If it doesn't, then it pumps it over to the controller. The controller is what we're going to do all of our coding in. That's what Ryu is. Ryu is an OVS controller. So the OVS host, or we'll call bridge, hooks up to the controller, and when it doesn't know what to do, it asks the controller what to do. And there are tons of different examples of these controllers out there in the Ryu source. We built our own, and this is a little bit of stuff from some projects that we've done at Rackspace. We had some of this comes out of that research, so it's all our custom code. It's just kind of dumbed down a little bit. Okay, so now I lost my train of thought. Sorry about that.
We'll talk after.
No, it's all good. No, okay, so the first thing that's going to happen is when the OVS gets spun up, it's empty. It doesn't know what to do at all. So there's two ways that you can handle this. You can either proactively tell the bridge, here's what you do when this IP address is assigned and someone wants to use it. And then you will then dump the flows down and associate that to a host. Or you can be reactive and say, hey, we know what to do with this host, but we're not going to tell the OVS bridge until a packet comes in destined for that public IP address. I'm going to show you both examples. First off, we're going to start with the proactive because it's the easiest. To me, that makes more sense, but there's arguments both ways. But just as one of the things we found is you want to implement both. Be proactive for speed, so you can pump down to your bridges, and so you don't have to ask the controller the first time the packet comes in. It knows how to route. But if you ever have to re-kick those bridges or something, the flows are gone, and so then they can be reactive at that point in time. So you don't have to manage when they go up and down. They just, the ones that are up get the flows. New ones come up. They'll ask for it later. Okay, so that's enough with slides. I know slides are boring, so. So let me show you the basics of the Ryu controller. So basically, you have a manager, and can you read that? Let me go to the presentation mode thing. Okay. So you have a class, which is your actual manager. So basically, this spins up and is listening for connections from your bridge. So there's two things that it can do. It can manage the flows, and then also can manage the database on OVS. It's called OVSDB. Basically, that is the database of all the assets that are inside OVS, the interfaces, the ports, the bridges, which allow you access to that. We're not going to talk about the OVS-DB stuff because it's not necessary in this example. But if you have a problem like that, you can talk to us. We actually built the OVS manager inside Ryu. So that would. Once this manager starts up, it does a few things right off here. It builds a little data repo. The data repo for this example is just storing the public IP address to the private IP address pairings. It's really dumb. It's just a dictionary. So I'm not going to show that. The next thing it does is it spins up a web service. So the web service is actually how we're going to interact with the controller to tell it, hey, this IP address needs to map to this IP address. And then the next two methods are basic events. So these are just events that happen in the OVS lifecycle. New connection is when a bridge spins up and connects to the controller, and it needs to know what to do. So there's a few of the lines in here are only necessary if you're using OpenFlow 1.0 with the nicer extensions. That's because there's some defaults that it has turned off that we need to turn on. So if you want more information about what I'm doing on some of this, talk to me afterwards. I'll be happy to explain it. But basically, it's when a bridge connects, we store that data path to the bridge just to store the communication mechanism. So when we get new packets in, we say, hey, here are all the bridges that are connected to us. Dump all these flows down, or handle these whatever we need to do with it down to all the bridges. For this example, we're only working with one bridge, but it's very simple to manage multiple bridges. The next down here, the other event we're going to work with is the packet in event. This is the actual message that happens when the bridge knows nothing what to do with the packet that comes in, so it asks the controller. That's all done inside here. So what we're doing in this example is we're parsing the packet, which is one of the powerful things about Ryu, is that it's got some great packet parsing. All that stuff's done for you. It's built into the framework. You don't have to worry about parsing the packet. We're only worrying about layer 3, so we're parsing the IPv4 address. If it doesn't have an IPv4 address, it means it's a layer 2. There's a lot of packets that go in and out, like all the ARP stuff and everything. I tried to disable most of those in the example, but some of them will get through, so we're just going to ignore all those packets that come in. So once we get an actual IP routing packet, we look at the public IP that the IP that it's destined for, which would be the public IP address, and we check our database to see if we know what to do with it. If we know what to do with it, we write the flows out. If not, we just ignore it for the time being.
So when you go from the inside to the outside, where are you? Is the disabling of IP just on the inside? Because you're just inspecting layer 3 on the IPv4, but what about with IPv6 if you're going to a public IP address like Comcast or Verizon or something like that?
This will support IPv6, but this example I'm just doing IPv4. But literally right here, you would change this to IPv6, and you could do both. But yeah, it does have full support for IPv6. I'm going to say put quotes around full support. We haven't tested all the IPv6 stuff, so. All right, then down here are just this is a method that I'll show you once we get to the API stuff. And this method's that one that I talked about earlier. It's actually setting, so flows, which I'm going to get into next, allow you to put them into quote-unquote tables, which are just stages that the flows can go through. And this enables that because it's version 1.0. Tables weren't fully supported till, I believe, 1.2. So, okay. So, let me show you the API real quick, and then. Okay, so this is the other part that matters, this is how we're going to interact with this controller to tell it what to do. So it is just a simple REST API. So we have, get the information about the public IP address, get all public IP addresses, and then create, which is just an association between a public IP address and one or multiple private IP addresses. So in the first example, it's just going to be a one-to-one mapping, but it does support the ability to map a public IP address to multiple private IP addresses, and it will determine which IP address to use based on a hash. So it's a simple load balancer in a way. It doesn't load balance based on a bunch of different metrics like more advanced load balancers are. It's really just a round robin, not round robin, but is a hash based on the data path information, which one it could go to. So it doesn't completely balance the load, but it allows you to have multiple private IP addresses, such as web servers or something like that, go to one public IP address. Now, I'll show an example of that as well. And that's all that there is for the API. So the one thing I mentioned before are flows. So flows are how OVS determines what's going to happen with the packet. It's not really the Python part of it, so I'll just go over it pretty briefly. But basically is when a packet comes in, each flow table is a set of rules, and you can resubmit to the next table or go to a physical output. Those are pretty much what you can do at the end of the flow. So it comes in, what our flow tables are, I'll show you real quickly. Crap, I lost my little browser thing on the side. Oh, shoot. I'm sorry. I don't have thought I had a script here with it. So when the IP comes in, first we make sure that it's coming in on the right port and that it's destined for a public IP address. If it is, then we move it to the next one to see if there are multiple flows. If there are multiple flows, multiple paths. So it could go to multiple private IP addresses. With that, we set a register bit based on to tell it which private IP address it is, and then resubmit to the final table. And the final table just looks at that register and says, oh, register 1 is this private IP address, register 2 is this private IP address, so it sends it out to the right output. And then it actually changes the destination on the packet to be the private IP address. And then when it comes back through, we reset the source would be from the private IP address. We reset it to the public IP address, so it works as it goes back out. That is all done how we write these flows in this flows.py file. I'm not going to go completely into this. There's a lot of the reuse specific stuff, and I'll be happy to if we have time at the end if you want. But basically, it's going through and it builds all the north to south, and when I say north to south, I mean public to private, and it builds those tables. So, for instance, here it's setting the rules that it needs to come from the northbound port, and it needs to have a public IP address, and then it sets its actions to resubmit to table 100, which would be the next table. Once you get to table 100, sorry, this isn't going to presentation mode. Okay, so at table 100, it goes to these multi-path flows. So basically, it has these actions, which are the output, and it's saying it's setting this register to either 0, 1, 2, 3, depending on how many private IP addresses you're associating this to, and then it resubmits to table 110. And then at table 110 here, it just checks to say which register it is, and that register will map to one of the endpoints. And that's just all done based on the value of the register is really arbitrary. Like if public IP address 1 would have multiple private IP addresses it's mapping to, will have the same register values in there. It's just based on the concatenation of all those values together would determine that. Okay, so let's show some of this in action here. All right, so to start up the controller is you need to, let me show you the, so if you're not familiar with virtual environments, when you're playing around with this stuff, get familiar with virtual environments because you're going to jack your system up several times with the different versions of Ryu and stuff that you have to pull down. So we're in a PyTexas virtual environment here. So stuff that's important that's getting installed really is this Ryu package. That was done by the requirements.txt. I think there's been a couple of talks about structure of your Python project. We're using the OpenStack templates, and basically it has the requirements file which tells it to install all these packages. One of them is going to be Ryu, which is important, and then Ryu installs a bunch of stuff, and then we have our app, which is this PyTexas 2015 app. So Ryu has two executables in it, I guess, and the Ryu manager is what uses to fire up and run the Ryu applications. So the command to do that would be Ryu-manager, and then what manager you actually want to start up. And so in our case, it's going to be this PyTexas.manager, which is that this class right here. So when we do that, it spits out a bunch of data. Now, there's other things that you can do with on the command line to fire it up. You can tell it which config files, logging, and other stuff. And for this example, I'm not going to worry about that. But you notice it fired up this REST API right here, which is listing on port 8080. Once again, that's configurable, but if you're not on 80, you have to run as root, so I don't really want to deal with that. And then, actually, first off, we're going to set up the Mininet. So what's happening with Mininet, if you're not familiar with it, it's basically building a virtual networking topology for you with multiple hosts, multiple bridges, and it wires everything up, which is awesome for testing this stuff. Unless you're trying to test tunnels, then don't use this. You can get it done with multiple actual physical VMs. We've been trying to get that to work. We haven't. So there we go. All right. So it just built a whole bunch of stuff. I have a pretty verbose output to show you what's going on, but really what it built is that topology that I showed you here. So it just built these two hosts, hooked them up to this switch. This switch is hooked up to here, and then it wires all that stuff up. And it also sets the controller for main to talk to the our controller that we just spun up. Now our controller isn't started. I shut it down, and so basically it's now waiting for that controller to come online, and it's constantly polling to see when that comes on. So when we switch back over here and fire this back up, you'll see a message here at the bottom. The bridge is now connected. So now we have full connectivity between the actual bridge and our controller. If you were controlling OVSDB, you would now get a whole bunch of stuff about all the OVSDB events that are going on, and it actually gets a lot of noise going on. So I didn't want to deal with that. So if we talked to the controller and asked for what routes were there, it's gonna tell us that nothing's there yet. Here we go. So currently we have no routes. So if we look over at the flow table, so this is getting into a lot of the OVS stuff. So I'm gonna go just breeze over a lot of it. Once again, if you have questions, we can answer any questions afterwards, because there's a lot of information that's going on here. But these are, right now we're looking at the actual flows that are in there, and there's nothing in there. So right now, this bridge knows nothing. If a packet comes in, it's going to go to the controller and tell it, I don't know what's happening right now. So we're going to tell it about a route here. So we go back over here, and this command is going to basically tell the it's just making a post to the REST API, and it's saying this public IP address 20001. Now that we're out of IP addresses, I don't know who that maps to, so don't try and route this, because I don't know, it might be someone. And we're going to map it to this private IP address. This is an array because once again I said we can map to multiple privates, which I will show you how to do in a second. So once that's done, we now go back over to our flow tables, and now we have a bunch of flows. So all this stuff is just stats about these flows. It's showing here the IP, so we're worrying about layer 3 at this point. If it comes in on port 1, which port 1 is our northbound port, I have not found a way to show actually port names of the ports in here. It's all port the OF port IDs. But you can get those names by using a lot of the other OVS commands that are in the slides. And the slides will be up on GitHub if you want to take a look at them later. And then it's making sure that the destination IP address is the one that we just told about. All other IP addresses, at this point in time, it's going to kick up to the controller and ask what to do because it has no idea. And then it's going to resubmit to table 100 right here. Table 100 then, since we only have one of the private IP addresses, it's doing this multipath on here. It only has one, so we only have one output then in table 110, which is saying if your register is 0, which would be the first one, change. We're going to modify the destination IP address, and we're going to outport to the southbound outport, and then the southbound switch takes care of routing it to the actual host, which would be done by basic ARP and or whatever protocol you're using underneath BGP or whatever to tell all your southbound routing stuff. Basically, that southbound route that we have, once again, is just an abstraction to say this is your normal routing for this particular physical topology here. So this would allow us to, this bridge would talk to and be connected up to multiple southbound switches into all of the different cells and data centers and stuff like that. So when we route down, that routing will then know what that private IP address belongs to. All right, so then if we try and ping it, so right here in Mininet, hpublic1 is just my public, is this guy right here. So basically I'm telling it, this is the host, and now run this command. So then you can run any command. So actually, you know what, I'm going to let it run infinitely here and show you a few things on the routing tables. So we're getting pings back. So what is happening? So as you can see, these are the number of packets that are being caught by each one of these flows. So the packet comes into here, it's modifying the destination. It goes then to the host, and the host comes back, and this is the return flow. So what this is saying, if the network source, if it's coming back from 172.16.1, then we're going to modify the network source to be our public IP address. And then so it's now being routed back out to the original caller saying that I'm coming from the 20.0.0.1. And then the pings work. So then I set all these up to have a little web server on them. So you could also do a quick little curl here on that guy, and there you go. Hello, I'm from VM1. So that's the who I routed that guy to. So this would be this guy right here is spawning with an HTTP packet backup saying with that text in it. All right. So what happens if we want to route that public IP address or a different public IP address? Let's use 20.0.0.2 to two different private IP addresses. Let's say we have VM2 and VM3 are now serving up the same website. So we can go back over here and make the same curl call, but instead, there we go. Instead, we're now going to assign two endpoints here, 16.2 and 16.3. So when we do that, we go back and look at the flows. Now we have a whole bunch of new flows. This is where these outputs are the important ones. So if you look at the registers here for both of these destination ports, now register 0 is set 172.16.2, and now register 1 is 172.16.3. So depending on the hash that happens at that multipath, it will set that register, and then now it's going to know which output to output it to. And so if we curl 2 from public 1, it actually hits VM2, So if we try and use the other public guy, let's hope this works. Yay. That hits VM theory. And that hash, you can actually tell it what type of hash to use. There's a couple of different ones. I think we're using a symmetric layer 3 hash. There are a few other ones that are in the OVS source, and that Ryu does fully supports those to program which hash you're going to use. All right, so the last thing I want to show you is the reactive side. So let's say you don't want to have a REST API up on the service. Why? I have no idea why you want to do it, but I'm sure there's a used case for it. Maybe your network admins don't let you run internal web servers or something like that. If that's the case, then you want to be reactive to it. Like so you just have a database setting up, and you have an app that puts them in the database, and this needs to read from it or something, or you put them in yourself or whatever. We can handle that as well. And so for this, I'm going to comment out two lines of code here. These 2 lines that I'm commenting out is when we get the association from the REST API, it actually writes the flows down. This is going to just ignore it. Say, okay, I'm going to make the association. I'm going to know about it. It's in our database, but I'm not going to actually write the flows down. So if I were to go up to Mininet and try and ping 20003, it's not going to work. Because we haven't done any route for that yet. So it just tries and tries, and then it times out, and we lost all the packets. So if we go over to curl and we tell it to, hey, let's route that to 4 and 003. Okay, now it's in our database. If we take a look at all of our routes here, we have 21, 22, and 23 here, all routing. But this is going to be okay. It's a lot of stuff to look at. But if you look closely, there are no routes to. There are routes to that. I forgot to restart Okay, now that we restarted, I'm going to dump the flows for this real quick. Okay, so now we don't have any flows programmed for that. We once again need to, because the controller, all the routes were in memory, all of our routes are now gone. By the way, that's not a good way to do it. Once again, it was just for a demo, so you want to put this in a database or something like that. So we're going to tell it about that route again. So now if we look at the routes, we have that route, but we should not have anything in the flow table. Okay. We have no flows. That's good. But if we try and ping that guy again, it's gonna ping. Yay, we got ping results. So what happened? If we go back to our flows, now the flows came in. So if we look at the logs for the controllers, not a lot, but we received a packet for that specific public IP address, and we had an association now, so we knew what to do with this. So we looked in the database, we got the pairing, and then we dumped the flows down. And then, so the packet was, what happens is it gets buffered on in OVS as it goes up to the controller. When the controller comes down, it writes the flows out, and now it knows what to do with that packet. Now, subsequent packets that come in, now we have a flow and a data path already built for that. So we only got the one request for 20003, because after it wrote the flows, it now knows what to do with it. And if we were to update that, and let's say, let me show you. So if I ask about it, it's for VM2. Let's say I want to, actually, it wouldn't work at this time. If you wanted to update it now, all the flow, and you wanted to reassociate it, that's the problem with the reactive pattern, is if you update your database and say this is now going to host 3, it's not actually going to tell the controller. So the controller is going to keep sending it to 4 until either the flows expire or you go in and physically eliminate them. That's why I said at the beginning you kind of want to have both, because if you're being proactive, when you got the reassociation, you would just dump the new flow down and it would overwrite the flow on OVS, and now it would automatically start routing it to the new packet, which I will demonstrate here. Let me uncomment this out. And I'm going to be smart this time and restart the controller. All right. Okay, so we have no flows on here. And then let's say we associate it to 4. And we go to Mininet, we ask about it, so it's on VM4. But now we want to reassociate that to a different endpoint. So we're going to say this is going to go to 3. Now when we we try and get that flow, it now pulls it from 3 because we had went down and rewrote the flows on OVS, and now OVS is routing it to the X1. So the question is, why would you do this? This is a very simple example, and you could get any type of basic router to do this type of stuff. The thing is, this is a very simple example. However, the OVS has a lot of powerful features that allow you to do very advanced routing stuff. However, having a controller allows you to control it ad hoc. So you can attach it up to the controller. You can control many of these bridges to do the same thing, and it allows you to be more dynamic about your how you want to route things without depending on someone else's platform. So you can program just do whatever you want it to, and you're controlling it now. And if there's not a feature on here, the nice thing is it's open source, you can add the feature or wait for the feature without having to pay Cisco $1 million+ to write a simple feature for you. Sorry, if there's any Cisco people here, I apologize. So that's really all I had. Is there any questions?
So software-defined networking is really popular for organizations like Rackspace and Amazon and Microsoft and whatnot. But do you see this technology coming down for smaller shops that maybe just have like a few racks of colo? It seems like a lot of the hardware that supports a lot of the Open Connect stuff is rather expensive networking gear. Do you see that becoming more popular as time goes on? Have you heard of any smaller, cheaper hardware that's going to support these platforms?
Well, OVS you can run on anything. I mean, it's Linux. So this right here I was running on Ubuntu 15. Ubuntu has it built in. Fedora, it's a easy install. So you could really run this in your colo and use whatever you want.
From a consulting perspective, what you're talking about is something makes dollars and cents to us, but smaller shops that would have to run it, they're going to have to hire somebody or consult somebody to work on their network. So it's probably a ways out, but it's a really good business opportunity for those of us in the now.
Yeah.
So just to kind of basically answer your question, a lot of your smaller shops are going to want something out of the box that just works.
Yeah, it may not make sense for that.
For now.
Yeah, and this is really designed for, or what we're showing here is really for the cloud, and the reason is because you don't know where your assets are belonging to. In that example, if you just have a small rack, you know where everything is. You have control over your switching infrastructure. If I spin up a new compute instance, I don't know where it's getting spun up with. And on the management side, on the Rackspace side, if you're asking me to reroute a public IP address to this private IP address, I now have to go find out where that that host now lives, and then I have to route it all the way up into through the route aggregation and everything, which is doable, but it's a lot of man hours. This allows that to be automated. That's the problem space that we're solving here. It would be for the much larger ones. However, it's if you have somebody within your smaller companies or smaller network infrastructures that knows how to do this, or you can afford to pay a consultant to do it. It's a lot of, you have a lot of flexibility.
Twofold question, kind of tying into him and something. So you've got your controller, which is say HSRP or VRRP, something similar to that, and one router goes down, where are you hard plugged in to where your controller is still able to access your network?
Well, that would be how you design your infrastructure. You'd want it to be HA. You would probably want multiple controllers hooked up and multiple bridges.
That's what I was
Yeah.
going to ask is, can you know, what's your ability to have kind of dummies and standbys, almost like a cloud controller amongst your PCs on your network running it? So,
Yeah, well, you can have, if you do it in a like an active passive standby, that's actually pretty easy. If you just, whatever the IP address is that it's connecting to, you can just, switch your DNS. I mean, not DNS, but where that IP address is routing to if one of your controllers goes down. Another thing is you can actually wire up multiple controllers to the bridge.
virtual machine, I'm assuming.
Yeah.
In your data center.
Sure, yeah.
Which would really clear that one up. Next question on OVS and Ryu and all that is, how is it handling VRF, virtual routing and forwarding, as far as, for your cloud services and your like data centers for your cloud storage and your hybrid storage?
Yeah, I can't answer that question. I'll talk to us afterwards. The smarter guys than I am will be able to answer that for you. So,
Does this handle VPN?
can you tunnel VPN?
Well, so you can put a VPN port on there, right? So like if you're running Open VPN or whatever,
Yeah.
the ton port there will just be a port. Anything you can like, so you drop OVS on a box and it basically forklifts the entire networking stack, and then you plug anything you want onto that bridge. So one could be a tunnel port, one could be a VPN port, one could be an Ethernet port, and then they all get OF ports, and you just write the flows to those.
Yeah, he's the guy to talk to. I'm more of the dev side on the DevOps type thing. So, any other questions? Okay, we're gonna talk to you afterwards. Then a couple gotchas real quick. OpenFlow 1.0 doesn't support tables out of the box. If you enable the Nicira extensions, you can. And I put the code up here. And put this on the internet because we spent a couple days trying to figure this out because there's no documentation around it, or there's documentation around it, just it's not very explicit on what you need to do. But basically, you need to bit shift the table that you're going to assign it to with the command that you send down to it. So whether it's an add, update, or delete for the flow. So that's just some stuff. Also with the layer 3 routing, remember I faked out a lot of stuff on here. So with the northbound and the southbound switching, I actually had it physically hard-coded to know to set the MAC addresses and everything like that for when you get the private IP address routes. But you need to make sure that you support or have a solution for ARP and anything else in the layer 3 stack. So it's doable. We have this running on a lot of or this type of system running on several of our services and stuff that so. It's very doable, and if you have any questions about it, feel free to talk to us or email us. My email is alanquillen@gmail.com or alan.quillen@rackspace.com. They're both on the front slide, as well as here's my GitHub. This is the source for all the demos are on GitHub, as well as my
They're on your GitHub page.
yeah, on right there, the very first top. That's the repository. And then they have the slides up there too. These are some of the web pages to find out more information. Ryu, the easiest thing to do when you're working with Ryu is get the source. I know you can pip install it, but really working from source helps find out a lot of the stuff that's not documented. Their documentation, Ryu's great, but their documentation is not very verbose, to say. And then find out more about OpenFlow at the opennetworking.org. And Mininet. Mininet's really cool if you want to play around with it. They actually have VirtualBox images you can just download with Mininet ready to go. It's also, if you're running Ubuntu, you can just apt-get install it, but not if you're running Fedora. So sorry if you want to play around with it and you're running Fedora. Won't work. All right. That's it. Oh, one more got you. I'm sorry. Attaching a controller I mean, the bridge to a controller, you have to use your IP address. Don't try DNS. That was about a couple hours of my day, one day, figuring that out. So, that's it. Oh, you have a question?
This is the first talk I've been to where it felt like somebody was speaking English.
Sorry, there's a question. That's all right.
How do you guys handle the risk for testing? Like, you don't want to accidentally introduce a bug which would cause the entire network to go down, right?
Oh, we've never done that before. Mininet for our development testing. We also have multiple infrastructure environments. We have labs and like a pre-prod type thing that will mimic our production environment. That is the one thing you need to think about is there is money to go into spinning up a second production-like environment, full production-like environment to really test it out. But
So is Mininet real similar to GN3?
I don't know anything about GN3.
GN3 will run like the actual operating system stuff. All Mininet does is a wrapper around OVS and network namespaces.
Okay.
And so when you have like that second host or whatever, that's just an IP sitting on a network namespace that has an OVS port.
Gotcha.
Yeah, so you can't like SSH it to the machine or anything like that. Cool. No more questions? Thank you. Oh yeah, Rackspace is hiring. So if you're interested in engineering jobs or development or DevOps, let me know. Or see our booth.